Recording is rolling. It's Thursday, April 20th. I've got a speed of light puzzle for you guys, and then I'm going to have you guys turn in that page that we've been working on last couple of days. Okay? So you guys remember last couple of days we've been solving these relativity equations, right? Okay. Okay. So you guys all have this page out? Oh, yeah, okay. So you guys have this page out. Now on the back side of the same paper is, oh look, it's this Fizeau experiment from 1849. Right, you guys see this? Right. Now, the way we're going to do this is I'm going to give you guys most of the class today to work in teams. That's why I have you guys in teams today, okay? To solve this puzzle. And then the last about 10, 15 minutes, the last bit of class, I'll go over the solution with you and see if you're able to crack this puzzle. Okay. So here, I'll read it with you. You guys can follow along. Okay. You guys got this in front of you. Okay. So this is a story I told you that this is how we started this whole this week, right? Right. I said people were trying to figure out what's the speed of light. This guy named Armand Fizeau came up with this idea of like, hey, let's have this cogwheel spinning. I'm gonna go out the field and spin this cogwheel, right? Bounce light off this mirror, and if everything aligns, then I can make certain calculations, figure out what's the speed of light, right? And that's okay. So that's the basic premise. Let's jump into this paragraph here. You guys can read it with me. In 1849, Hippolyte Fizeau, also Armand Fizeau, see both names, same guy, okay, accurately measured the speed of light by spinning a toothed wheel. I've been calling it cogwheel, tooth wheel, same idea, right? Something like that. A beam of light would pass through one gap, right? Gap in the teeth. And if the wheel was spinning fast enough, then after being reflected back, the beam would hit a tooth adjacent to the gap so that the reflection of the light source would become not visible behind the wheel. So we're over here, we're looking at the reflection, right? Now, if it's not spinning at all, then that beam light just goes here and back and we see the reflection. Okay, great. Okay. But if it's spinning fast enough at just the right rate, then again, we're behind the wheel looking over here, right? Then if, say, like this tooth has moved over to take the place of this gap, right? Which is not very much. It's just like a few degrees, right? Right? If it's just moved this far, I'll call this theta, right? That's theta. That's how far it's moved. Just that little sliver. Right? Then if it's done that in the time that this light goes to the mirror and back, then any light that would have hit the tooth and hit a tooth in the first place, it's not going to go and reach the mirror at all. But any light that would have gone through a gap and bounces off the mirrors, comes back and hits a tooth. So now you can't see the reflection of the light. Right? You guys got that? See how it works? Okay. Any questions about the mechanics of how this is set up? All right. So a little bit more here. I gave you guys some numbers, and the question is, how fast does he have to spin the wheel? Now, the way I'm asking you this question is I'm having you solve it backwards of what he was solving. See, what he was doing was he was just speeding up spinning the wheel until he reached the correct angular velocity, like the spin rate, you think, like how fast is it spinning, so that all those mechanics that we just went over click into place and you can't see the reflection and say, aha, I can use that to determine what the speed of light is, right? Now, I'm having you guys do this backwards because you guys know what the speed of light is. We're in the 21st century, right? So that's the first number I gave you. I gave you the answer to his question, right? So here's the speed of light. Usually I call it 3 times 10 to the 8 meters per second. I went ahead and just gave you a bunch of digits, right? So 299792458 meters per second. You guys see that? Okay. I also gave you the distance to the mirror, right? So from the wheel to the mirror, there's some distance here, right? I gave you the diameter of the wheel in centimeters. Notice these units. I gave you the distance to the mirror in kilometers. I gave you the diameter of the wheel in centimeters. Right? Let me throw you guys a big old hint here. Do you guys think that it might help at some point to convert those into base SI units? Like here, all these leading questions on the right side are all like meters and seconds and radians, right? Right? So think about that. Right? And I also gave you the number of teeth on the wheel, right? Now, everybody has different numbers. Your numbers are probably different than mine. I mean, how most papers go, right? Okay, you guys get all that so far? Right. And the question that I'm actually asking you guys is, how fast did he have to spin the wheel? So suppose you know all these values, and you're going to hop in a time machine and go back and tell him the answer, like, hey, here's how fast you should spin the wheel. That is the answer to this box, right? Again, he had the backwards version of he figured out how fast he's spinning the wheel, therefore he can calculate the speed of light. But if you know one, you can figure out the other, right? Right. Everybody good so far? Any question? Right. So let's go over some hints here. I want to help okay. You guys out a little bit here. So, first hint, one method of solving uses only 3 of the 4 provided values. So see, I gave you these 4 values I just told you about. Turns out you really only need 3 of those to solve this question. One of them ends up canceling out, although, depending on how you go about it. Right. Okay. So just an idea right there, right? There are a little bit different ways to go about solving this problem. Okay? The next hint I gave you says this right here. X equals theta times r. Okay. Guys, remember maybe from elementary school, circumference equals 2 pi r. Circumference equals 2 pi r. Right. Circumference equals 2 pi r is a specific version of this more general formula. X is how far a point on the edge of the wheel moves, maybe how far a tooth moves, like in meters, right? Theta, guys, what does theta represent in this context? And I labeled it up here. It's how far the wheel turns. It doesn't have to turn very much, right? Maybe I've been saying a few degrees, but really, what is the proper unit for theta in this context? You don't want to use degrees. You want to use radians, right? Radians, right? And what does r represent? The radius of the wheel. Here, let me show you guys the turntable. Right? You guys remember this turntable rotating? Right. If it's rotating at a constant rate, that's called a constant angular velocity. Ooh, I might call that omega. Curly W looking thing, right? That's okay. And look at these 3 Roosevelts. Right. The further out they are, the faster they're moving in a linear context. Right. Like one right near the middle. If you point a radar gun at that guy, it's pretty close to 0 meters per second. But the guy on the outside, maybe there's like a tooth on the outside of a tooth wheel. I'm moving like pretty fast. Right, so you guys get that? Right. That is what this expression says. And the expression right beneath it says linear velocity is equal to angular velocity times radial distance. Okay, so sorry. The first of those 2 formulas is for how far something's moved. The next one is how fast. Right, and sorry, that's what I was just explaining. Right. So, right. So say you're looking at this Roosevelt on the outside. That represents a tooth on the wheel. Right. How far does it move? X. How fast is it moving? V. Right. But in an angular context, there could be theta and omega. Okay. Right, you guys got that? Okay. Good so far? Good so far? Okay. Let me throw another hint on the paper for you guys. Okay. Guys, 1 revolution. Right. 1 revolution is equivalent to also what? How many degrees is that equal to? Yeah, 360 degrees, right? Now, do you want to be using degrees today? No. But you want to be using what again? Radians. How many radians is 2 pi? Right? You guys ever heard? Okay. Actually, I should guess that circumference equals 2 pi r. Right? It's like a version of that. Okay. So 2 pi radians. So if this were to make a complete trip around, which it's not going to go nearly that far, but if it did, that would be 2 pi radians. So radians. Okay. Right, you guys get that? Okay. Now, here's how you can do it. Again, a little bit different ways to approach this, but I gave you guys a bunch of leading questions on the right side. If you answer these questions one by one, and you're getting them correct as you go down the page, there are different places where you can break out, like either at the end or possibly somewhere in the middle, where you can break straight to the answer and you can figure out how fast it's rotating, which is an angular velocity. Maybe I should say this: omega equals. You're like solving for omega, right? Right. Radians per, that's what radians per seconds measures. Okay. Right. You guys good with that premise? Okay. So this is a real challenge problem. Gotta think about the mechanics of how would this all go together. So again, I'm gonna let you guys work in teams for a good amount of time here, and then let's say about 20 minutes or so, maybe 20 minutes, a little over 20 minutes, and then I'll pull you guys back together and I'll go over the solution with you guys and see how you did.